Good morning, dear colleagues. I'm Rory from the Computer Science Department at the University of Colorado, Colorado Springs. Like you, I wish that we were actually in Casino Berea, Biarritz-France, where we could passionately argue after our talks about our mathematical theories, lemmas, and postulates, all while looking over the Bay of Biscay. But alas, here we are in the ether. I present to you a means to mathematically formalize the multidimensionality of human consciousness as it interacts with the logic of the brain, by utilizing rough set theory and Riemannian covariance matrices. Now, we all know that René Descartes postulated, "I think, therefore I am," inferring that the mere act of thinking about one's existence proves that there's someone out there doing the thinking. Nowadays, there are many established theories of self-consciousness phenomenology, and I will review them briefly in a minute. But for now, let's transform Descartes' 17th century formal logic into 21st century computer architecture. So he's saying that something out there is observing the thinking, or, as you'll see in my research, a separate operating system is observing the artificial intelligence, and like humans, it can veto or override the AI's resultant or output. To review the theoretical definitions of consciousness, I have a link below of a full video on this matter, but for this 10-minute video, here's a synopsis. In computer science, we generally use functionalism to integrate sentience into AI. Mathematicians model consciousness with theories such as situation, calculus, and combinatorial complexity. Computational neuroscientists and neurosurgeons measure consciousness by degrees of brain stem injuries, awareness, and degrees of electricity in the brain that define brain death, coma, vegetative state, etc. Neuroscientists follow forms of neural Darwinism that rejects dualism, such as their neuronal correlate theory. Neurobiologists focus on forms of cortical recordings. Physicists link consciousness to atoms and quantum coherence, and philosophers view consciousness non-mathematically, as in their spread the mind theory. 99% of the money, as in billions of dollars each year, directed at artificial consciousness is linked to the military laboratories in the US, China, and Russia, where we're designing artificial consciousness for humanoids. I am part of this world, and I would like you to consider the publicly available use case that we use to evaluate our artificial consciousness. A mother is standing in front of her house in a meadow. Her house is on fire, and she can hear from within the house her 2 infant children screaming out for her to rescue them. Her brain has mathematically calculated that the burning roof will collapse at any second, and there's nobody there to help her. Her consciousness not only overrides her brain's output, which is that she will surely die if she runs into the house, she also forces it to do the exact opposite as to what its AI compiled. Her consciousness forces her brain to make her body run into the house, rescue her children, and run out with them. And of course, we've all heard many real-life stories like this ad nauseum. So, from a predicate calculus standpoint, we are going to be agnostic to all the aforementioned theories of consciousness because they are all observing what is being calculated in another part of the brain, or atoms, or quantum spaces, or other dimensions, and so on. And it's totally okay for them to continue down this track, but what we want when synthesizing consciousness is to simply have a separate system, like all these theories do, that will analyze, agree with, or veto the brain, as in human or the AI and machine. From a human point of view, we do this anyway. Most advanced societies mandate that no matter how brilliant or intellectually challenged a person is, each soul is afforded an equality of being. Similarly, no matter what artificial consciousness we have, it should also have to be agnostic as to whether its AI system is as trivial as a toaster or as complex as Lincoln Labs TXG-AIA. So let's start by defining a one-dimensional state of artificial consciousness, because it's easy for us to assimilate that it is generally accepted that people have a bivariate perspective. When life is stable and good, the odds of committing an immoral act are low. Conversely, when life is perilous and unpredictable, the odds are higher. For example, a mother will not consider killing her newborn baby. However, in the Nazi concentration camps of World War II, thousands of Jewish women who knew they would be killed if they became pregnant, who upon becoming pregnant from the SS guards raping them or allowing rape, overrode their hardwired synapses to nurture their babies and immediately killed them upon birth. Here we see a covariant linear relationship of this tragic phenomena, and we can compute the covariance and homogeneity of the psychoanalysis of consciousness. Conversely, We see a non-linear relationship when assessing financial morality and financial state, where there's no covariance, there's no pattern. Some indigents are saints, while others use their financial plight to justify stealing. Conversely, billionaires, some are philanthropists, others use their fortunes to sow corruption and deceit. So table 1 over here shows data in the 3 dimensions of artificial consciousness with psychoanalytical experiments where a cohort of 53 subjects undertook 3 sets of morality tests. The first test queried where they would, when they would morally justify murder, as shown in the covariance matrix table of table 1, where x1 murder on the y is the point that they would murder, and x2 murder underscore s on the x is the environment, shown in figure 3a. Similarly, questions for coveting were asked, and we see a partial covariance matrix in the scatter plot for covariance between the linearity of the murder question and the non-linearity of coveting questions, as shown in figure 3b. The entire covariance matrix as a scatter plot is seen in figure 3c. The issue is that the complexity of consciousness is complex. The challenge is to data mine and extract classifiers across millions of conscious dimensions. My hypothesis is that Riemannian covariance matrices are specifically made to handle an infinite amount of dimensions, and rough sets are made for machine learning because it can measure degrees of uncertainty with its upper and lower bounds in an XY clustered setting. For a large set of rough set samples, I needed to trace how dependent variables y relate to independent variable x, as depicted by the 2 vectors traversing all these dimensions here in figure 4. So to connect all these dimensions to a 2D Euclidean space, I tested equation 2, where the 2D curve C is defined by a set of ordered real numbers squared, and for a 3D curve, I simply use an ordered triple set, as set forth in equation 3. Note that this comma here indicates the intersection of these 2 surfaces, and it is this that creates a 3D parameterized curve in a multidimensional space of real numbers, where gamma takes the parameters t and maps it to an ordered n-tuple of real numbers, as defined here in equation 4, where both alpha and delta are real numbers. My challenge was to find a way to express the parameterized mapping of a vectored gamma t, where all its elements represent separate coordinates. Equation 5 solved this because I could trace gamma as a function of time. Now, to smooth this function, or to make it infinitely differentiable, I took f of t on the open interval alpha beta, so long as its derivative existed, and then differentiated across all the individual components, resulting in equation 6. The issue, however, is that Riemannian theory utilized manifolds, not curves, and a manifold is a topological space that locally resembles Euclidean space near each point. Said differently, each point of an n-dimensional manifold has an immediate neighborhood that is homomorphic to the Euclidean space of dimension n. So to calculate the distance on a manifold, we use tangent space of the manifold at point x, meaning, and this is the cool part, as we hypothetically travel on the surface of the manifold's curvature, so in figure 5, we pass through the point x with vectors of magnitude and direction, and these vectors are tangent to the manifold. So in 2014, Chen et al. Tested the viability of Riemannian classification using 3 types of classifier: kernel SVMs, logistic regression, and partial least squares, to explore learning methods for multidimensional vector spaces on Riemannian manifolds, where in my case, each of my vector spaces will be a facet of a machine's artificial consciousness. However, I will have already calculated all the necessary locations on the upper and lower bounds using rough sets before passing each singular dimension onto the Riemannian system. This means I only have to test my SVM classifier in the kernel space using equations 7 and 8. The distance between 2 rough set upper and lower bounds is now calculated by mapping the Riemannian manifold to Euclidean space using Chen et al.'s Mercer kernels and Lovett et al.'s projection kernels, which yields a covariance between the 2 subspaces as shown in equation 9. I then use a radial basis for each rough set graph on the curve in figure 6 in equation 10, and lastly, I test its viability using equation 11. And actually, since this paper, I'm using some other methods too. This is ongoing. I'm still seeing some artifacts and spikes where there should be none. Not sure if it's my code or my equations. It's probably both. Thank you for your time. I hope when we meet again, it will be in person. And I'll be happy to answer any questions at this time.